Hi, my name is Vincent Guy. This video is a tutorial on LASPATED software. LASPATED stands for Library for the Analysis of Spatiotemporal Discrete Data, and it was implemented in collaboration with Anton Clayvate, Giovanni Amorim, André Mazal, and Victor Hugo Nascimento. What motivated the development of this software is a project I am coordinating which has two main objectives. First, the development of a chain of software for emergency health services. And second, the development of artificial intelligence, operations research, and statistical tools for the optimized allocation of ambulances to emergency calls. For this last goal, the optimized allocation of ambulances to emergency calls, we are interested in several interesting research topics, such as the calibration of models for ambulance travel times, the development of models for survival function, of models for emergency calls to emergency health services, and of course, the development of models, but also of solution methods for this optimized allocation of ambulances to calls. We are working on this project in collaboration with Rio de Janeiro Emergency Health Service, and in the context of the development of models for emergency calls, we had access to the history of calls to Rio de Janeiro Emergency Health Service for the years 2016 and 2017. For this process of calls, we developed models, statistical models, and tools. Regarding the models, we believe that these models are somehow new, especially when coupled with adaptive discretization methods that I will mention in the end of this tutorial. And we thought it would be useful to provide a software for the calibration of such models. The description of these models can be found in the paper we wrote on LASPATED software that is available on arXiv. Regarding tools, as I was saying, we also developed new tools for the analysis of our stochastic spatiotemporal data, which are the emergency calls. These tools are space and time discretization tools. Since we could not find available in libraries the space and time discretization tools that we needed, we developed them, and LASPATED also provides the user with these tools. It is interesting to note that our models can actually be used for more general stochastic spatiotemporal processes. For instance, the process of crimes, or of robberies, or fires, and so on. More generally, model events with a timestamp, location information, plus possibly additional features. In this tutorial, I will first focus on the description of the functionalities offered by LASPATED. More precisely, I will first describe the space-time discretization tools provided by LASPATED. I will then detail the models we proposed for stochastic spatiotemporal data that can be calibrated with LASPATED. The second part, I will show you how to use these tools through Python, MATLAB, and C++ code examples, and taking as an application, as an example, the calibration of models or emergency calls to Rio de Janeiro Emergency Health Service. Finally, I will provide ongoing research directions on adaptive discretization and on the treatment of missing data. Our intention is to enrich in the future LASPATED with precisely tools that could deal with such adaptive discretization and missing data. The library is public, and external contributions to extend it are welcome. So, in the first part of this tutorial, of this presentation, I will focus on the functionalities and the methodological aspects of LASPATED, explaining in particular the statistical models that we propose. And in the second part, I will show you how to use the tools offered by LASPATED through Python, MATLAB, and C++ code examples. So let me start in the first part of this tutorial with the description of the space-time discretization tools provided by LASPATED. And to start with, I will use as an example the stochastic process of emergency calls to Rio de Janeiro Emergency Air Services. The study of this process motivated the development of LASPATED library. So consider this process of emergency calls, Rio de Janeiro Emergency Air Service. Every call is characterized by its time, its location, which is given by a pair latitude, longitude, and its priority. The priority is an integer between 0 and 3. So typically, we have calls for which no ambulance is required. And then we have calls for which an ambulance is required. And among these calls, we have calls of low priority, intermediate priority, and high priority. So here I am showing you on this slide the first 10 calls for 2016 to Rio de Janeiro Emergency Air Service. You can find the corresponding CSV file on the GitHub webpage of the project. And in this CSV file, you have in the first line the description of the columns. The first column gives the datetime information. So we first have for every call the date of the call. Then in the second column, the time of the call. Then in the third column, the priority of the call. And then finally, in the last two columns, the location information, longitude and latitude. So for this type of spatiotemporal stochastic data, we used the following modeling. We discretized in space and in time. So for instance, for the discretization in space, we could discretize the city into a 10 by 10 rectangle, so into 100 rectangles. And for every sub-rectangle, every subregion I, and for every time window T of the time discretization, and for every call priority P, we assume that the process of calls has some is Poisson with some intensity that depends on the subregion, on the time window of the time partition, and on the call priority. So in this context, we had two main objectives in LASPATED. First, how to discretize in space and time our data. So we have to count for every time window of the time partition, every subregion of the space partition, and every call type. We have to count the number of observations that we have and the number of calls that we have. And then we proposed ways of calibrating the intensities of the Poisson processes. And we actually proposed two methods that I will describe in this presentation. So as I was saying, LASPATED stands for Library for the Analysis of Spatiotemporal Discrete Data. As of July 2023, it offers the following modules. We have the Python time discretization module. We have Python space discretization functions. So these functions allow us to count the number of observations for every subregion of the space discretization and for every time window of the time partition. And we will see that LASPATED offers several possible space discretizations and several possible time discretization. Then, as I was saying, we assume that the observations for a given subregion, time window, and arrival type are Poisson with some intensity, and we propose two ways of calibrating these intensities. And LASPATED comes with a MATLAB module that calibrates the intensities of the Poisson processes, and a C++ module that does the same in C++, that calibrates the intensities of the Poisson processes. You can download LASPATED on this GitHub page, and you can either clone or download the source code. Let me now be more specific about the functionalities of LASPATED. So given spatio-temporal observations with space, time, and possibly other attributes, the library offers five main functions. So first, for space discretizations, it allows the user to define a spatial border. We can define three types of borders, either a custom map provided by the user. For instance, it can be in the context of our project where we were interested in the emergency calls to the city of Rio de Janeiro. This border can be the border of the city of Rio de Janeiro. A second type of border that can be used is a rectangular border containing all the data. And finally, we can also use the convex hull of data. The second module offered by LASPATED is space discretization, and we offer actually three types of space discretization: in rectangles, in hexagon, and customized. The third module offered by LASPATED is the module of time discretization, and we will see that we propose several types of time partition, time discretization. And once space and time discretization is done, LASPATED will count the number of arrivals for every subregion of the discretization, every time window of the time discretization, and every arrival type. And finally, we propose modules, a MATLAB module and a C++ module for the calibration of the stochastic models that we proposed for this stochastic spatio-temporal discrete data. And as I was saying, we have the assumption that we have Poisson processes with intensities that depend on the subregion, the time window, and the arrival type, and the calibration modules computes these intensities. So more precisely, what LASPATED does for the space-time discretization is the following. We have our spatio-temporal observations with possibly additional features. So in the case of our motivating project, we have the history of emergency calls. For every call, for every arrival, we have the time instant. We have a time instant, the timestamp for this arrival. We have the location and possibly other attributes. And LASPATED will compute what we will denote by NCIT, the number of observations for every arrival class C, every subregion I of the space discretization, and every time interval T of the time discretization. It will compute also for every arrival class C, every subregion I, and every time window T. It will compute the number of arrivals that we will denote by MCITN for observation N, and this combination CIT of the arrival class, subregion, and time window. And finally, it will compute MCIT for every CIT, which is the number of arrivals for arrival class C, subregion I, and time window T. Now, let me present you more in detail the functionalities of LASPATED regarding time discretization and space discretization. Now, actually, for space discretization, we have already said that we offer three possibilities: discretization in rectangles, hexagon, and customized. For time discretization, we also have three possibilities. The first one is to use periodic time windows with elementary time windows of equal lengths. So, for instance, we could have time windows of 30 minutes during the week. So we could have a model which is periodic with period 1 week and elementary time windows of 30 minutes. The corresponding time partition would be Monday from midnight to midnight 30, Monday from midnight 30 to 1 o'clock, and so on until Sunday, 11:30 p.m. until midnight. The second type of time partition that is allowed by LASPATED is periodic, but with different elementary time windows, with elementary time windows of different durations. So, for instance, we could have a model which is periodic with a period 1 year, and we could have as elementary time windows the first 3 months, then the next 4 months, and then the next 5 months. And finally, we can define a customized time partition. For instance, the previous partition could be refined considering time windows of 30 minutes for days which are holidays and days which are not holidays. So we have, for instance, for Monday, all the time windows of 30 minutes during the day for Monday holiday and Monday that is not holiday. And the same for all the other days of the week. And we could, as another example of customized time partition, we could refine the previous example, adding the possibility to include a spot event. So, for instance, in this situation, we would have 4 types of time of elementary time windows. So, observations of time windows of 30 minutes on days which are holidays, and for these days which are holidays, either the spot event is scheduled or it is not scheduled. And observation on time windows of 30 minutes which are not on holidays. And again, for these days which are not holidays, either the spot event is scheduled or it is not scheduled. So we have 4 types of time windows of 30 minutes. So these are the functionalities offered by LASPATED for time partition, time discretization. Now I give you an example. I have shown you on the first slide of the presentation, the first 10 calls to Rio de Janeiro Emergency Service in 2016. So here we have represented these 10 calls on the map. You can see on this map the city of Rio de Janeiro. And here we are defining as the border, as the region containing the observation, the border of the city. We use a discretization in rectangles, and we have represented the 10 calls. And in green, we have, so the 10 calls are represented here in red. And we have also represented with green numbers the index of the time partition. So here we assume that we have a discretization in time windows of 30 minutes. So if we go back to the history of calls, we can see that the first call here is at 2 o'clock, 9 minutes. So this is the fifth time window of 30 minutes. The indexes start at 0, so the index of the corresponding time window of 30 minutes is 4. And you can indeed see here that the lowest time index is 4. So indeed, in green here, we have represented the indexes of the time windows of 30 minutes corresponding to the time partition. And you can also see the space discretization in rectangles. So here we are illustrating several things: the definition of the border, the space discretization, and time discretization, time windows of 30 minutes. Continuing on this discussion on the definition of the border, which is, if you recall, is the first topic that I mentioned, functionalities of LASPATED here, definition of the border. We were mentioning that the first type of border that we can use is custom map. Here we took the city of Rio de Janeiro. We could also define as the border a rectangular border that contains the data, and this is what we do here. So here, for our same motivating example, emergency calls to regional emergency services, and here on this figure we again consider the first 10 calls in 2016. We consider as the border, as the studied region, and the region containing the data, a rectangle that contains the data. And we discretize this rectangle into 100 rectangles with indexes from 0 to 99. We represent again here the calls in red. And if we remember, the third way of defining order, studied region, is to consider the convex hull of the observation, and this is what we do here for the same data. So here we have represented the convex hull of observations. We have represented again in red the calls, and we have discretized again this region into rectangles. Now here we provide another example of space discretization, which is a discretization in hexagons of the city of Rio de Janeiro. Here the border is the city of Rio de Janeiro, and we discretize in hexagons. And here, finally, I am going back to the previous figure that I had shown, where we illustrate actually all the space-time discretization process. We define as the border the city, we discretize in space in rectangles, and we also do a time partition in time windows of 30 minutes. And as I was saying, here we have the space-time discretization information represented with the rectangles of the space discretization represented with their indexes inside the rectangles. The border is the city, and we have also represented in green the indexes of the time windows. And as we have seen, the lowest of these time indexes is 4. So if we recall, LASPATED will compute those numbers MCITN, MCIT. MCIT is actually deduced from MCITN. So MCITN, we recall that this is the number of arrivals for observation N, for arrival class C, region I, time window T. So for the example of the 10 calls that I have represented, only some of the CITN are activated here. And actually, we have 10 calls, so we have 10 numbers here for the MCITN. The N is 1. We are interested by in the first observation here. And here I have, for all these 10 calls, I have provided what are the values of the CIT. And there is no repetition, so there is a 1 here on every line. No repetition of the triple CIT here. So here for this first line, M01641 equal 1. means that for the first observation for core of priority 0 for rectangle with index 16 and time window of index 4, for the first observation, we have observed 1 core, and so on. Now, I have finished with the description of LASPATED space-time discretization functions, and I would like to present you the calibration of the intensities of the Poisson processes that we propose. As I was saying, we assume that the MCITN are Poisson with some intensities lambda CIT. So we can compute the likelihood of the corresponding model. Here in this model, we have denoted by dt the duration of time window t. We can simplify the likelihood if the intensities are the same for some time groups. If we have groups of, if we have a partition of the time intervals, and in a given group in the partition, if all the intensities are the same, then we can simplify the above likelihood. Now, more generally, if we have groups of time windows, maybe we would not like to have in those groups of time windows, in a given group, we would not like to require that the intensities are the same, but we would like to require that the intensities are close to each other. For instance, we may want to, if we have time windows of 30 minutes, we may want to require that the intensities for all the days of the week between, say, 5 in the morning until 8 in the morning are close to each other, but not necessarily all the same in all these time windows of 30 minutes within this time window. So the first model that we propose to calibrate the intensities is a model that minimizes the opposite of the log likelihood plus some penalizing terms that penalize the deviation of intensities into time windows that are in some groups where we would like the intensities to be close to each other. And also, we penalize large deviations of intensities for some subregions. So, for instance, we may require that intensities in neighboring regions are similar. So, we have a similarity regularization function that is actually the opposite of the log likelihood plus some quadratic term that will penalize deviations of the intensities between some pairs of regions and between some time windows that are in the same group. So if we look at the loss function that we would like to minimize to compute the intensities lambda CIT, we have the opposite of the log likelihood. And then the quadratic terms are, we have time groups G, that are time groups of a set of time groups big G, and the penalization for the deviations of intensities into in the time groups is as follows. For a given group G, we have penalization WG, and the quadratic term is WG over 2, the sum of lambda CIT minus lambda CIT prime squared for the T prime in J. So here we, for a given group G, we want the intensities to be close to each other. So the larger the WG, the closer the intensities in group G. And similarly, we have a space penalization. So for pairs of region I and J, we have a penalizing term Wij. And if Dij is the distance between I and J, the penalization in our quadratic term for space regularization is Wij divided by 2Dij times the square of lambda CIT minus lambda CJT. So we would like here the larger Wij divided by Dij, the closer the intensities will be in regions I and J. So this is the first optimization problem that we solve for the calibration of the Poisson intensities. Actually, these intensities are non-negative, and we solve this problem using projected gradients with line search along the feasible direction. Now I will show you a second model that we propose for the calibration of the intensities. This is a model with covariates. So I recall that lambda CIT is the intensity of the Poisson process for arrival type C, zone I, and time interval T. So for this triple CIT, we define some covariates, and we denote by XCIT the vector of covariates. And we consider the linear model. So lambda of XCIT dt is the duration of time window T. This is a linear function, beta T transpose, of the regressors, of the covariate values. So beta T transpose XCIT. The intensities are non-negative, so we must have that the beta T transpose XCIT are non-negative. So to facilitate this model, we will denote by n the total number of observations, and by mn the number of arrivals for observation n. Then in this situation, the negative log likelihood that we need to minimize to calibrate the beta, and therefore the lambda, knowing the regressors x. So the negative of the likelihood function is the sum over all the observations of beta transpose xn minus mn log of beta transpose xn. The corresponding problem is a convex optimization problem that we solve again by projected gradients. Now I will give you an example of this model with covariates. And this is this example, actually, that we implement in LASPATED for the model with covariates. And I will illustrate this with the process of emergency calls. So consider a time discretization of every day of the week into time windows indexed by some indexed T, taking values 1, 2 until capital T. So for instance, we could have time windows of 30 minutes for every day. And so we would have capital T equal to 48, number of time windows of 30 minutes during the day. And a given time window during the week is defined by a pair dt, where d is the index of a day and t is the index of a time window during the day. So here we have a model which is periodic, with periods 1 week. And for every day, we do again a partition into time windows, into 48 time windows of 30 minutes. So we index the set of arrivals. We denote by E the set of subregions. And we consider for every subregion I a vector of regressors xi. So in LASPATED, xi can have any size, but in the context of our project, xi had the following elements. So the first entry of xi was the population count in zone I, And the next entries were the areas of occupational land use of a certain number of land types. And we also denote by D a set of indexes containing both the indexes of the days of the week as well as indexes for holidays during the year. Therefore, the cardinality of D is 7 plus the number of holidays. So this means that actually we will have intensities for the days that are not holidays, and every time window of 30 minutes, and every subregion and arrival type. And then for the days that are holidays, so for every time window of 30 minutes, every subregion and arrival. So now we have two indexes for time discretization. The intensities now are denoted C lambda CDTIN for arrival type C. DT is indexing time windows, so D corresponds to day or holiday G. T is the index of the time interval. I is the index of the zone, of the subregion, and N the index of the observation. So this intensity is a linear function of the regressors. So it is beta CD T transpose Xi. So we can write, as before, for this model, the likelihood. And LASPATED will compute the beta, maximizing the likelihood, adding the constraints that this beta CDT transpose Xi need to be non-negative since they correspond to intensities. So in the context of our project, where the first entry of beta CDT is a proportion of the population of a given zone involved in calls of type C for day or holiday D and time interval T. Since this is a proportion, it should not exceed 1. So these beta CDT of 1 are between 0 and 1. As I was saying, the beta transpose Xi should be non-negative because they correspond to intensities. So what LASPATED solves for the calibration of the model with covariates is the minimization of the loss function, which is the opposite of the log likelihood, while requiring that the beta CDT of 1 are between 0 and 1, and the beta transpose Xi, the Poisson intensities, are non-negative. And actually, to have a problem that is differentiable on the feasible set, we can, without a loss of generality, reformulate problem 2, replacing beta CD transpose Xi greater than 0 by beta CD transpose Xi greater than epsilon for some epsilon positive sufficiently small. This reformulation is a convex problem, as I was saying, with differentiable objective over the feasible set, and it was solved with projected gradient with line search by LASPATED. And to project and to solve the problems in projected gradient, along the iterations of the method, we use the Gurobi. So to summarize, for the calibration of the intensities, here are the two optimization problems solved by LASPATED. For the first calibration, we minimize this penalized likelihood function. So we have two functions actually for the calibration. The first function that, given the weights Wj, Wij, will compute the lambda. So it will solve for given penalties this optimization problem. And then we have a cross-validation function that, given candidate values for the weights Wj and Wij, will compute optimal values given by cross-validation for these penalties. And LASPATED calibration module also solves for the model with covariates this optimization problem 5 in variables beta CDT. So it will compute the beta CDT, solving this problem by projected gradient with line search along the feasible direction.